Hi everybody, this is Arif. Today I'll solve 5 math questions on mathematical induction. For those who have just learned mathematical induction, this would be a good practice. Okay, the first question says prove that 1 times 1 factorial plus 2 times 2 factorial plus ... all the way to n times n factorial is equal to n plus 1 factorial minus 1. And the n here can take values like 1, 2, 3, 4, 5, right? Positive integers. So mathematical induction says that we should have a basis, right? Like the base condition. So what is the base condition here? N is equal to 1. So we check n is equal to 1, whether it satisfies this equality. So 1 times 1 factorial, is it equal to 1 plus 1, which is 2 factorial minus 1? Is equal to 1? Yes. So it checks out. So then we will assume that this also holds true for n is equal to k, right? So what does that mean? 1 times 1 factorial plus 2 times 2 factorial plus ... So k times k factorial is equal to k plus 1 factorial minus 1. So I assume that this also holds true. So the next step is to check whether n is equal to k plus 1 also holds true. Okay, based on this assumption, what I'm going to do is I'm going to add one more term here. So 1 times 1 factorial plus 2 times 2 factorial plus ... plus k times k factorial plus, then I have k plus 1 times k plus 1 factorial, right? So this is my p k plus 1. Okay. So now I already assume that this is equal to k plus 1 factorial minus 1. So this is equal to k plus 1 factorial minus 1. Then I have plus k plus 1 times k plus 1 factorial. Okay. So this is going to be equal to, so k plus 1 factorial, parentheses, if I do that, I have one of those here, 1, and I have k plus 1 of those here, so plus k plus 1, minus 1, I have minus 1 here. So this gives me k plus 2 here. So what is k plus 2 times k plus 1 factorial? It's just k plus 2 factorial minus 1. Or actually, we prove that this also holds true, this relation also holds true for n is equal to k plus 1, right? Because if I put k plus 1 here, on the right hand side I got k plus 2 factorial minus 1. Okay? So the proof is complete. Let's move on to the next problem. Okay, in the next question they ask, prove that n to the 5th power minus n is divisible by 5. For n is equal to 1, 2, 3, 4, 5. It goes on like that. Okay? So the base condition, well, we can pick n is equal to 1, but n is equal to 1 is kind of trivial. So 1 minus 1 is 0. 0 is divisible by 5. So let's also check n is equal to 2. So n is equal to 2 is 2 to the 5th minus 2. This is equal to 32 minus 2 is 30. So this is divisible by 5. So we can actually safely take n is equal to 2 as our base condition. Now we are going to assume that, the second step, we're going to assume that k to the 5th minus k is divisible by 5. So what I'm going to do is, I'm going to call it, let's say, 5m. So m is some integer, right? So then k to the 5th minus k is divisible by 5. This is my assumption. So let's look at the k plus first term. So k plus 1 to the 5th power minus k plus 1. Okay, let's see what this thing gives me. Okay, for those who don't remember how to expand it, so we remember the tree here. So this is 1, 2. This is 1, 3, 3, 1. So it's going to be 1, 4, 6, 4, 1. And this is 1, 5, 10, 10, 5, 1. This is good. I have 5s and 10s. They are divisible by 5. Okay. So 1, 2, 3, 4, 5. The 5th power here. So this is going to be k to the 5th, right? Plus 5k to the 4th plus, then I have 10k cubed plus 10k squared plus 5k plus 1, right? Then I have minus k minus 1. Good. So this is equal to k to the fifth minus k. I have that term. So I got this one and this one. So 1 cancels that one. This is good. And then plus 5 parentheses. I have k to the fourth plus 2k cubed plus 2k squared plus k. Okay? So I already showed that, I assume that this is divisible by 5. This is like 5m. And let's suppose this is like L, right? Because k is an integer. So in the end, it's going to be an integer. So L is an integer, m is an integer, and they have factors of 5. So in the end, I can write as 5 times m plus L. So this is nothing but 5 times z. So you can call this as another integer. So in the end, we show that when n is equal to k plus 1, okay, this is also divisible by 5. By assuming k to the fifth minus k is divisible by 5. So this completes the proof. Okay, the third question says prove that cosine x plus I sine x to the power n is equal to cosine nx plus I sine nx. So here, a quick reminder, I here is the imaginary number, so I squared is equal to minus 1. Okay? And here n is taking values like 1, 2, 3, 4, 5. Okay, we are going to use mathematical induction. So the base condition, when n is equal to 1, cosine x plus I sine x is equal to cosine x plus I sine x. Okay, so this checks out. Our assumption now, we are going to say cosine x plus I sine x to the power k is going to be equal to cosine kx plus I sine kx for some k. Okay? So we assume that this holds true. So we're going to check n is equal to k plus 1 term. So when I put k plus 1 here, I will have cosine x plus I sine x, okay, to the power k times cosine x plus I sine x. And this is 1, right? So this is k plus 1. Okay, so let's expand it by using this assumption. So we already know that this thing here is equal to cosine kx. Let me write it down. Cosine kx plus I sine kx, right? Times I have cosine x plus I sine x. So I need to multiply them. So this is equal to cosine kx times cosine x. Seems like in the end we're going to use some trigonometric identities, right? And then I have, let's look at the real terms first. So I have I and I have I. So I squared gives me minus. So it's going to give me minus sine kx times sine x. Okay, so this is my real part. Plus I. Okay, I have sine kx times cosine x. So sine kx times cosine x, and then I have sine x cosine kx, so plus cosine kx times sine x. Good. So this is nothing but like cos, sine, sine, right? Cosine, this gives me cosine. Since this is minus, I'm going to use plus for cosine. Kx plus x, so which is k plus 1x plus I. This one is sine cos, cos sine, so it's going to be sine, okay, kx plus x, which is k plus 1x. And as you see, we prove that cosine x plus I sine x to the power k plus 1 is equal to cosine k plus 1x plus I sine k plus 1x. So this actually completes the proof, right? So I put k plus 1 here and I got k plus 1 here. Okay? For n, based on this assumption. Okay, so we are done with the proof. Let's move on. So here comes the next question. prove that n factorial is larger than 2 to the n. So here n runs from 4 and all the way up. So as we see, n is equal to 1 does not hold true, right? So 1 factorial is not larger than 2 to the 1. So if we check all the way to n is equal to 4, right, doesn't hold true. So n is equal to 4 is going to be our base condition. Let's check if n is equal to 4 is true. So when n is equal to 4, we have 4 factorial. This is larger than 2 to the 4. Is this correct? So 4 factorial is 24. 2 to the 4 is 16. So yes. So n is equal to 4 is true. So this is going to be our base. Second, we are going to say that n is equal to k. For n is equal to k, this also holds true. So k factorial is larger than 2 to the k. This is our assumption. So the next step is to check n is equal to k plus 1 term. Okay? So by the way, since n is 4, 5, 6, goes on like that, so k must be larger than 4, right? We already checked n is equal to 4k, so I'm going to pick k something larger than, it can be larger than 4. Okay? So n is equal to k plus 1. So k plus 1 factorial is going to be equal to, it's going to be k plus 1 times k factorial, right? So when I check here, k is going to be larger than 4. That means that k plus 1 is definitely, right, k plus 1 is definitely larger than 2. And we also assume that k factorial is larger than 2 to the k. Right? We already made that assumption. So this thing is obviously larger than 2 times 2 to the k, which is equal to 2 to the k plus 1. So we conclude that k plus 1 factorial is also larger than 2 to the k plus 1. So this completes the proof. Based on this assumption, we show that this is also true for the k plus first term. Okay? So let's move on to the next question. Here comes the next question. For real x which is larger than minus 1, we will prove that 1 plus x to the power n is larger than or equal to 1 plus nx. So here n is equal to 1, 2, 3, 4, 5, it goes on like that. So let's check n is equal to 1 case. So it gives me 1 plus x to the power 1. Is this larger than 1 plus x? Yes. So it holds true, right? So when you check n is equal to 2, it will also be true. N is equal to 3, it will be also true. But we want to prove it, right, for any n. So this is our base case. So we will assume that 1 plus x to the k is also larger than or equal to 1 plus kx. Okay? So this is our assumption. In the next step we are going to calculate, we're going to find 1 plus x to the k plus 1. Okay, so what is that? So it's going to be 1 plus x to the power k times 1 plus x, right? Good. So 1 plus x to the power k is actually larger than 1 plus kx, right? Larger than or equal to. So we can simply say that this is going to be larger than or equal to 1 plus kx times 1 plus x. So this term is the same, but I know that this is larger than 1 plus kx, so it's going to be larger than this thing. This whole thing is going to be larger than this thing here. Okay? Here, okay, I was able to do it because I know that 1 plus x is positive, right? X is larger than minus 1. So if x is larger than minus 1, x plus 1 is larger than 0, right? So this is what I actually used here. Okay? So the inequality sign didn't change direction, right? So this is a positive number, this is also a positive number, and 1 plus x to the k is larger than 1 plus kx. So it works out well. So what is the right hand side now? So I have 1 plus x plus kx plus kx squared, right? Good. So this is going to be equal to, I have x plus kx here, right? So this is going to be 1 plus x parentheses, I have k plus 1 plus kx squared. Good. So this term here is also a positive term. So I can simply say that this is also equal, larger than or equal to, right? 1 plus k plus 1 x. Okay? So I prove that, I show that 1 plus x to the power k plus 1 is also larger than or equal to 1 plus k plus 1x. Okay? So instead of k, I can put k plus 1 here, right? This is the proof. So we are done with this proof as well. This actually proves that due to mathematical induction, 1 plus x to the power n is larger than or equal to 1 plus nx, requiring that x is larger than minus 1. Okay? I think this is all for today. I hope you enjoyed it. We will solve more problems on mathematical induction later. Until then, take care of yourselves and see you later.